Hello everyone, I'm Armin Vedadghavami from Northeastern University. Osteoarthritis or OA is a joint disease characterized by cartilage degradation in response to upregulation of several catabolic factors. Despite discovery of promising OA drugs, none have been approved for clinical use. Since OA is a localized disease, drugs have to be injected directly into the intra-articular space of the knee joint. However, the drugs suffer from short joint residence time due to rapid synovial fluid turnover. Additionally, drugs fail to penetrate through the dense avascular matrix of cartilage, which is comprised of a dense meshwork of collagen type 2 and a high density of negatively charged aggregate glycosaminoglycans or GAGs. However, this high negative fixed charge density of cartilage presents a unique opportunity to use electrostatic interactions to enhance transport of drugs into cartilage by making them positively charged. The concentration of cationic drug carriers at the synovial fluid cartilage interface is enhanced by a factor K known as Donon partitioning coefficient. This enhanced interface concentration creates a higher concentration gradient, resulting in faster diffusion rate along the cartilage thickness, as well as high uptake. The net positive charge of the carrier has to be optimized to enable full thickness penetration using weak reversible charge interactions in order to reach the high density of chondrocytes in the deep zone of cartilage. However, too high of a positive charge will hinder the diffusion of carrier due to strong binding interactions. Here, we designed short-length cationic peptide carriers or CPCs of the same size but with varying net charge to investigate how the net charge and its spatial distribution can affect their transport in normal and arthritic cartilage, which has a lower fixed charge density. The CPCs were designed through manipulating the number of arginine residues separated by alanines as spacers to obtain sequences with net charge between +8 and +20. Uptake of CPCs in cartilage increased as we increase the charge from +8 to +14. A further increase in charge decreased the uptake of CPCs, showing that uptake does not monotonically increase with charge. The binding of CPCs +14 to +20 with cartilage was strong enough to maintain retention for 7 days when dissolved in PBS, while CPC +8 ultimately diffused out. Explants were then dissolved in high salt concentration to break the charge interactions. Consequently, more CPCs diffused out, but the retention rates reached a plateau after a few days, suggesting contribution of other types of interactions in addition to charge interactions. CPC +8 rapidly penetrated through the full thickness of cartilage due to weak reversible charge interactions, while CPCs +14 and 16 took 24 hours to penetrate the same depth. However, CPC +20 was stuck at the superficial zone due to strong binding that hindered its diffusion in cartilage. This data reinforces that weak reversible binding is necessary for carriers to penetrate through the full tissue thickness. We then treated cartilage explants with trypsin to deplete the GAGs and stimulate mid and late stages of OA. In mid-stage arthritic cartilage, where 50% of the GAGs were depleted, uptake of CPCs dropped, highlighting the important role of charge interactions. However, the uptake of CPCs remained very high in the late stage even when most of the GAGs were depleted, suggesting presence of other types of interactions specific to arginines such as hydrogen bonds and hydrophobic interactions. These results validate that CPCs can be applied for targeting mid to late stage arthritic cartilage. To delineate the role of hydrophobic interactions from charge interactions, we used two lysine-rich CPCs of same size and charge, but one with a hydrophilic asparagine tail termed as CPC +N, and the other with a hydrophobic phenylalanine tail termed as CPC +F. We observed that the uptake of hydrophilic CPC +N reduced to less than 1 upon GAG depletion. Additionally, CPC +N completely dissolved out of cartilage under high salt concentration treatment, together confirming the dominant role of charge interactions. However, incorporation of the hydrophobic group in CPC +F significantly enhanced cartilage uptake and retention in both healthy and arthritic cartilage. These results suggest that charge interactions can be stabilized by hydrophobic interactions. In conclusion, we observed that electrostatic interactions significantly enhance transport rate of cationic carriers in negatively charged cartilage, while hydrophobic interactions synergistically stabilize the charge interactions. CPC +14 showed the highest uptake, rapid, and full thickness penetration, which along with its biological safety, makes it an ideal drug carrier for targeting cartilage. With that, I would like to thank the funding sources, Department of Defense and NIH, and thank you for your time.